sorry about that. I think something went weird with the internet, so I'm just gonna restart it completely. So, anyway, starting from, yet again, the beginning. Let's look at limits. And yeah, I'm gonna record this and put it on YouTube right afterwards. So, what limits do is they tell us about the value of a function as the input approaches a certain number. So, let's say we have a function, let's just call it f of x. And we're looking at the behavior of the function with this condition over here. So, what exactly does that mean? That really just depends on what you're looking at. So here, this is the limit as x approaches a of f of x equals L. That means the behavior of the function at or near x equals a. Alright, and then when we have that little minus sign, what that really means is you're looking at the behavior from the left. So from the left of x equals a. And then here, that plus sign means from the right of it. And then the infinity and negative infinity, that basically means what's happening to the function toward infinity. In other words, you can think of this as the right end of the function in a way. So remember the term end behavior? Yeah, so toward the right end. So that just that literally just means infinity. Or toward negative infinity. Again, with the same type of thing, you can think of it as the left end of the function. Okay, sorry, just saying a quick remind, telling people that I'm restarting the stream, but anyway, alright, so let's continue on this and just look at connections with this and other stuff. Okay, so, one of the main behavior connections that would be easiest to look at is just end behavior and horizontal asymptotes. So essentially what happens with those, remember earlier when we talked about horizontal asymptotes, what I mentioned was you can find the degree of the numerator denominator and just compare those two. And the end behavior, that I just said, look at the far right and the far left, what happens to the function. So here, we're going to really unpack that and see what that actually means. Okay, so if you look over here then, sorry, I think I just realized that my volume was really low. I just turned it up again. Sorry if it was low before. If it was low before, I'm just going to get the video and dub over it. Anyway, so end behavior tells us about what's happening toward the far left and right. In other words, the limit as x approaches infinity and negative infinity. Horizontal asymptotes basically tell us the same thing. If you need me to go back to anything specific, please tell me where to go. Otherwise, I'm not gonna do it because I don't know where to go. But yeah, so hopefully this doesn't lag too much. Anyway, let's just continue on then. So basically what we're doing is taking the limit as x approaches infinity. Usually the limit as x approaches negative infinity is the same thing. So you usually only have to check one side. The only instance where you would need to check both is like usually trigonometric stuff, like inverse trig stuff, because you're gonna see interesting things happen there. Okay. I'll just scroll back up there for right now. I mean, you should already have this written down, but here it is. I'll leave this here for 5 seconds as you take a picture. Okay, 10 seconds. Alright. Anyway, so now I'm gonna go over something that I'm pretty sure you haven't gone over before. Like more of a trick to do rather than any concept. Okay, so I'm gonna multiply 1 divided by x to the 3rd power to the top and the bottom. I'm gonna make that a bit smaller so I can actually write that clearer. Okay, you might be wondering why in the world am I doing that. The reason is because we want to look at certain relationships. You'll see the relationship when I do that. So notice I'm writing limit again. Always write it until you substitute. Okay, then you'll get 2 plus 1 over x squared minus 1 over x cubed, all divided by 5 plus 2 over x minus 1 over x squared plus 1 over x cubed. Okay, so we can evaluate each of these limits individually. So notice that this and this do not have x in them, so that's just going to be 2 and 5 on its own. So I'm going to draw the fraction bar here. And the question is, what happens with the rest? Okay, 1 over x squared. If we were to allow for x to go toward infinity, so this number becomes extremely big. Question is, what is that going to be? So 1 over a gigantic number, basically that's going to be 0. So you can think of that as adding 0, and then minus 1 over big number. Same idea, so that's just still minus 0. Notice that these are just number over gigantic number. So same idea is going to happen, and you just get 0 minus 0 plus 0. So then you end up with 2 over 5, and that's actually the horizontal asymptote. So technically you should write this. So let's look again back at horizontal asymptotes from the past. And remember I said find the degree of the numerator, find the degree of the denominator. It's 3 and 3, right? And if that's the case, then if they're the same, then what do? No, we do not divide 3 and 3. That literally makes no sense. Because then you would just get 1 every single time. What you divide is this. The leading coefficients. Because basically what it's saying then is that you have 2 functions growing at the same rate. So this 3 is that rate. And the only difference between them is one is growing twice as fast, one is growing 5 times as fast. So same growth rate, but just like within the same growth rate, basically. So what we can do is just divide those. The reason is, well, we've done this work here. Divide by 1 over x cubed, 1 over x cubed. And the only thing that doesn't die out is those 2 numbers when you let x go toward infinity. So a lot of what we're doing in this problem is just straight up logic rather than necessarily here's a process to do. But let's say, what if we actually instead had this thing as a 2? So let's get rid of that. What if we did this, for instance? Then what that would mean is here we're going to get the 5 over x because I chose the largest power, which in this case would have been the 3. So you get 2 divided by a bunch of zeros, which is actually going to make this thing go to infinity. And the reason for that is because you're going to get 2 over 0, basically, which approaches infinity. It doesn't equal infinity, mostly because infinity is not a number, and this doesn't necessarily equal anything anyway, but it approaches. And just a quick thing, this arrow, that means approaches, not equals. So when you're doing your work, I'm going to mark you down if you do write arrow when not appropriate, or equals when not appropriate. Anyway, let's go on to the next part. Okay, continuity. So the general idea of it is you can draw something without picking up your pencil or pen or whatever you're writing with. For instance, continuous, not continuous. The reason is not because of stopping. Do not ever use that word in math because that actually doesn't have any meaning whatsoever. The only place you would really ever see that is with traffic flow, but that's talking about the traffic flow, not about functions. Yeah, I just want to address that because that's something I've heard a lot in class. People say, oh, the function stops. Then I ask, what do you mean by that? Then no one can answer it because it doesn't actually have mathematical meaning. So, just want to put that out there. Don't do that. I'll probably mark you down for writing the word stop, especially because I told you not to. So, let's look at the formal definition. You will need to use this. Actually, if you get into college and take calculus there, you're gonna have to do that too. So, yeah. Anyway, let's get working on that then. So, what does this mean? The limit exists. That just means the function approaches a number. And here, f of a is defined. That just means the function has a value there. So this means that the function value and what the function approaches are the same thing. So if you look at it that way, so like this last part over here that I wrote, if those are the same, then the function is continuous. If you remember it like that, then you'll remember, okay, so function approaches something, I have to have a limit. Function value, I have to evaluate the function somewhere. The function has a value there. Alright, so let's kind of work with some of these concepts. Since I just kind of talked about concepts, we're going to go into the average rate of change and everything later on with concepts. I just figured it'd be easier to group it this way. Anyway, so let's graph. I know that for our class that is the weak point, but that's why it's important to go over it and really do it more. Because obviously the stuff that you already know, the stuff that you're already comfortable with, you're already good with, so you don't need to practice as much. But the things that you're not comfortable with, the things that don't make you feel good about yourself, that's what you gotta practice. This is coming from experience in the practice room as a musician and teacher, but yeah, that's mostly where I learned that lesson. Anyway, let's start graphing then. So here, tangent inverse. Let's think, what does that thing look like? Well, this is actually just one of those parent functions, so that should be something that gets memorized. So if it isn't memorized, then please memorize it. So the main thing that you probably wouldn't remember is like, what exactly are the points? So let's just say that's 1, 2, alright, and then I'm just gonna make, let's see, 1, 2, 3, 4. Let's just do it there. Pi over 2. And here, 1, 2, 3, 4. Negative pi over 2. And then those are horizontal asymptotes. And that's what we get. So, end behavior. So what's happening then is, as x approaches infinity, so imagine like you put a little bug on here and had it move toward x equals x approaches infinity, like toward the right. What's it going to get closer and closer to? The horizontal asymptote. So your y value approaches pi over 2. What about as x approaches negative infinity? Imagine, same thing. You put a bug on the curve, have it move toward the left. What y value is it getting closer and closer to? Again, the horizontal asymptote. So in this case, you get y approaches negative pi over 2. Alright, so what about the horizontal asymptotes? You can easily see them in the graph. That's going to be y equals pi over 2 and y equals negative pi over 2. So notice that the end behavior and horizontal asymptotes basically the same thing. Alright, so let's move on to the next one. Actually, okay, I'm going to move on, so I'm going to give you 5 seconds to take a picture if you need to. Alright, let's move on to the next one. Okay, so this one, yeah, I know there's a reason why people requested this, because for whatever reason, last unit didn't go so well. The logs weren't very good, but doesn't matter. We'll start anew, and this time you'll get it. So, logarithm. So remember, this is not IN. If you ever write that, I'm probably no, not probably. I will be marking out points. If you ever write 1N, I'm marking off even more points, because I've already told you that's an L. So, anyway, Ln. What does this look like? The parent graph basically looks like this. There's a vertical asymptote there, and this intersects at 1. So, let's graph this thing. Actually, well, in order to graph it, we need to figure out the transformations, right? So, where are the transformations? We have this 2, this 1, and this 1. So, you get marked down quite a few points if you just write this as just like, I've seen people label these and call them things but not really do anything with them. So what you have to do is exactly what I'm doing here. So I'm just going to color code these to make it a bit easier to follow. Okay, so what's this yellow thing doing? This is a vertical, and I'm just going to say a scaling by 2. So what does this do to all the points to the graph? So you multiply y, every single y by 2. Alright, so what's going to happen then with that 1? With the 1, that's a horizontal shift 1, and then in what direction? That's actually going to be left. So that's going to be, you subtract 1 from the x values. So horizontal means x values, so subtract 1 from x values. Okay, what does this other 1 do? So there's a vertical shift, obviously by 1, but question is which direction. In this case, it'll be up. So that means you're going to add 1 to, okay, so it's vertical, that means y values. Add 1 to the y values. Okay, so the question is, what are we talking about with these things that we're multiplying and subtracting, adding from? So, let's look at the reference points. So that just means the important points and asymptotes that you're going to need to graph the parent function itself. Okay, so we know that there is an x-intercept at, in this case, it'll be 1, 0. And then there's actually going to be a point e, 1, because ln of e is 1. And there's a vertical asymptote at, where is it? At x equals 0. So then with that, we're able to start graphing this thing. So now we know that we're going to be doing stuff to these. What are those things? We're going to be multiplying by 2 to all the y values, and then we're going to shift the thing. So I like to do it this way. So what are your scaled points now? You're going to take each of these and you're going to scale them with the scalings. Here we only have one scaling, so cool. Just have to do one thing. So what is that one thing? It only works on the x values, so the y values, they stay the same. The asymptote is an x value, so that changes. Well, it's supposed to change by 2. But it's multiplied by 2. What's 0 times 2? Still 0. Or it's 1 times 2? Oh, sorry, that's the y values. Why did I do that? Yeah, let me change that real fast. So the x's stay the same, the y's change. So here, 0 times 2, still 0. 1 times 2 is 2. Alright, now let's shift the points. Okay, and then what you end up getting here then is... Let's see. So here, both of them are changing. So for the x values, we're going to subtract 1 from them all. So from this, we take out 1. So 1 minus 1, 0. This is going to be e minus 1. Just write it like that for now. 0 minus 1 is negative 1. Alright. And then final thing. Adding 1 to all of the y values. So 0 plus 1 is 1. 2 plus 1 is 3. Alright. So, let's look at how this is going to get graphed. So notice this did take a while, but the thing is, this doesn't actually take that long of a while. I'm just explaining it while I'm doing it, because I know that y'all need it. But yeah, so. When you're graphing, I'd say the longest time you're probably going to spend is making the axis. But please don't just try to waste time when you're taking a test by drawing the axis. You're probably not getting points for that. You're getting points for the actual content. If you get any points, they're not going to be that relevant unless you're able to do the actual graph itself. So, learn how to graph is good for you. Anyway, let's look at this. So, we see we have a vertical asymptote at x equals negative 1, so let's just draw an asymptote. And we have the point 0, 1. And it, okay, e minus 1. What's e again? E is about 2.7-ish. So subtract 1, you get 1.7-ish. So 1.7-ish, 3. Like that, more or less. And then you can kind of figure out that it's going to look something like this. Alright, so original question, what's the end behavior? What happens as x approaches infinity? Y approaches, so imagine you put a bug on here. What's happening as it keeps moving toward the right? It just goes toward infinity. In other words, it just keeps going up and up and up and never exactly stops. So y approaches infinity. How about as x approaches? So saying as x approaches negative infinity doesn't actually make sense because this thing doesn't go past -1. So let's just say its left limit. As x approaches -1, y approaches. So again, imagine here's a bug. What's happening as it keeps getting closer to the asymptote? This thing keeps going down, so this goes toward -infinity. What about horizontal asymptotes? There are none. So remember, horizontal asymptotes tell us about whether the function converges towards something or not. In this case, it definitely doesn't. So, yeah, you can literally see it from the graph. And it's important to be able to see and interpret that from the graph as well. Alright, so let's move on to practicing some more stuff. Alright, so use the graph to evaluate the indicated limits. I should have said and quantities because there's a few non-limit things going on too. So. Whoops, clicked the wrong thing. What's happening as x approaches 3 from the right? So where is x equals 3? That's this area. So what's happening? We see from the right, so that means we're going to look only at this part. If we kind of put a bug on there, we see that as the bug gets closer to the asymptote, this thing's just going to keep going down and down and down. So that would be -infinity. Here, from the left, so imagine we put a bug around here, toward the left, and it just keeps going and going toward the asymptote. That's actually also going to be -infinity. But the question is, at 3 itself, is the function approaching anything? It's not approaching any one number. This actually does not exist, though. So, don't write equals. Instead, just write dne. So I put unbounded. That's a standard abbreviation for unbounded. If you want to just write bounded, that's just the same thing without the un. Surprise, surprise. And this means because. So because unbounded. So you can write that. Okay, so the next 3 problems might look the same, but they're actually different. Make sure you're noticing those little details of, hey, look, there's a negative in front. So let's locate -3. Alright, that's over here. So, as x approaches -3 from the right. So let's look at the right-hand side of that. So here's -3. What's happening on the right? So imagine there's like a bug over here. As it goes toward -3, what y value does it hit? It's expecting to hit y equals 1. So we can write 1 there. And then next we can ask from the left though, what happens? It's expecting to hit. Also make sure you read the axis correctly. As you can tell here, that is 1, that is not 2. You will get marked down for that as well. Because I skipped 2 units there. I won't always skip 2 units, it's just, it made sense for this graph. For visuals. Here, that is actually going to be 2. So, this is 2. What about exactly at -3? Does it approach anything? It doesn't approach anything specific. So in this case as well, dne, and the reason is, this is because left-hand limit is not equal to right-hand limit. So please don't just memorize these letters. Make sure you know what they mean, and make sure you connect those words to meaning. So again, I'm emphasizing meaning here. Don't just write that phrase down for fun. I've seen that a lot. Okay, so what about f at -3? Exactly at -3 is just going to be that point. That's -3, comma, -1. So what this equals is -1. Okay, so let's look at limits toward infinity then. As x approaches -infinity, what happens to the function? So as the function goes toward the far left. Just keep going that way. What happens? It gets closer and closer to the asymptote, which is 2. How about toward infinity? Same idea. And notice it's approaching the asymptote still, from the bottom, but still the asymptote. Okay, now this one might be a bit tricky if you've been doing what I said not to do, which some people might have been. And so what I told you to not do is just think, oh, I have to put a bug on the left and the right of something. No. That's just a visual aid. So let's look at around x equals 0. So around x equals 0 is this. What value is the function getting closer and closer to as you get closer and closer to x equals 0? Another way you can kind of look at this is like, imagine you have a circle, and you just make the circle smaller, and smaller, and smaller, and it's getting smaller toward that point. And if it actually gets small and then turns into a certain point, then that means the limit exists. That's what it is. So in this case, that would be 2. Oh, wait, I'm so sorry. This is supposed to be 3. I read that wrong. Yeah, so sorry about that. If you had confusion earlier as to why I wrote 2, good, you were thinking you can read a graph. Alright, anyway, how about let's look at as x approaches 4. So here's 4. Let's just see if we just look over here. Is there a point? Oh, hey, look, there's an actual point. What is it? 2. 4, 2. So that equals 2. So that means f of 4 itself also equals 2. Alright, cool. Okay, so I have a few questions here then. Is the function continuous at -3? Let's look at it. So at -3, we have these things going on. So does the limit exist? No. Does the function value exist? Yes. But is it continuous? No, because the function is not approaching the function value. In fact, the function is not approaching anything. So no, because the limit as x approaches -3 of f of x does not exist. So that could be one reason. Because remember, look back over here. I'll scroll back down, don't worry. Limit has to exist. The reason why? It has to approach something. If it doesn't approach anything, obviously it's not going to be continuous. Because you can't draw something that's not continuous. Like that. Okay, how about at 4? We can look at this. So x approaches 4, it exists. F of 4, it exists. Are they the same? Yes, they equal each other. They're the same. So, you don't just say yes because. I mean, on the test I'll actually ask you why, so you have to explain as well. So you can say the limit as x approaches 4 of f of x equals 2, which is equal to f of 4 as well. Cool. Let's check this thing now. Now you don't have the limit in a graph form, you have to do it. So, oops, 1. Why did I write 0? The limit as x approaches 1 of f of x. Let's not write f of x. Let's just put the actual function itself. E to the x minus 1. What should you always try with a limit? Direct substitution. So, put the 1 in there, we get e to the power of 0. which is, so remember that is not undefined. A lot of people think that for whatever reason, but that equals 1. If you need to review that, go back to the video on exponents. So let's look at f of 1 itself. Some of you probably have already noticed that if you have the limit existing by direct substitution, you've already checked the function value. But I'm just redoing it for those who haven't quite realized that yet. So, there's that. So we see that the function value exists, the limit exists, and they are the same. So you can say, yes, that was supposed to be a C. Because the limit as x approaches 1 of that equals 1, which is the same as f of 1. Alright. So, now let's do this thing. Let's do limits again, graphically, numerically, and analytically. So numerically means by table, analytically means algebra. Graphically obviously means with a graph. So let's graph this thing. So, how can we graph this thing? Well, we have an x squared on top, so no, this is not a parabola. The top part alone is, but the whole thing itself is not. But usually when you have an x squared like that, what you're going to want to do is factor it. So that's going to be... let's see. Is that what I wanted it to be? Oh, I think I meant I wanted that to be minus. Oops, let me change that real fast. Because that's going to give us x plus 2 times x minus 3. That's what I wanted. Sorry. Let me just change that real quick on all of these, because I did that on all of these. Anyway, so I'll change that on the rest when the time comes. Anyway, so what happens then is x plus 2 and x plus 2 divide out, and we just get x minus 3. So the function is just x minus 3. However, there's one small thing that happened. There is a hole. There's a hole at x equals 2. At negative 2, sorry. Alright, so anyway, what does x minus 3 look like? It's a line. So there's a line with slope 1. Shifted. Down 3. So this is what it originally looks like, basically, but it's shifted down by 3. So 1, 2, 3. So I'll start over there and then just continue like this. Hopefully I can draw a pretty straight line, or at least close enough for stream purposes. Yeah, cool. Good enough for stream purposes. So the question is, what's happening at x equals negative 2? So, actually, that was a big erase. Let me just draw that a little bit more better. Yeah, like that. Okay, so at 2 itself, let's see what we get. Negative 2, go down there. By the way, there's actually a removable discontinuity here, or a hole, so that should be there. Alright, so the value is negative 5. So the thing that's interesting about this is that the function doesn't actually exist there, but there's a prediction for what it would be if it were to exist. So by looking at the graph and analyzing it, you see the limit as x approaches negative 2 of the function equals negative 5, actually. Alright, give you 5 seconds to take a picture if you need to. Alright, let's move on down here then. So, numerically, and let me just erase the part that I messed up on. So let's just... Yeah. Okay, so you're gonna need a graphing calculator or like some sort of calculator power for this. So x squared minus x minus 6 divided by what was it? X plus 2. Actually, I'll just show you exactly what I'm doing, so I'll add in the screen so that you can see what's happening there. So another window capture. And that'll be decimals right there. Alright, so if you look at what I'm doing, I've typed the function in like that, so I'm just going to get the values into a table. Actually, wait, I didn't need to do that. Sorry, whoops. So sorry, that wasn't necessary, but we can look at this. So we're looking at x going toward -2, right? So what we can do then is look at what happens at -2.1. How about -2.01? Sorry, that's supposed to be 0. -2.001. -1.9. -1.99. -1.999. So we can see a pattern going on here, right? So we see that we get toward negative. So -5.1, -5.01, -5.001. So from, at least from the left, we see that we're getting more and more toward -5. What about from the right? Well, same thing, right? We see that as we get closer and closer to -2, the function's getting closer and closer to -5. So I'd say to just kind of do this on your own, to check that again if you need to. And here, we have the values. I just kind of snuck that in there as you were looking at the other thing. But yeah, so just from the table alone, we can already tell we will get -5. Okay, so let's move on. Oh, and basically, the question probably would be, how do you choose these numbers? You simply just choose them by thinking, what am I trying to get closer and closer to? Oh, there was a question as to how we know there's a hole there. The reason is because you are dividing something out. And so remember, for limits, whenever we factored and divided things out, we still got an actual number. The reason for that is because that's actually a hole. So there's a thing that is approaching, even though it is not actually the function value itself. Okay, so moving on to the next part. How to do this analytically. So how to use algebra. Okay, so, oh yeah, gotta modify that part again. Sorry about that. So here are the strategies. As I've listed before, direct substitution, just always try it. If it doesn't work, try something else. In factor, you can figure out conjugates, and you can use other algebra related things as well. Okay. So in this case, this is pretty clear that you're going to be doing factoring because we literally already did it. So there's the factoring that we did, dividing it. Then we get the limit as x approaches -2 of x minus 3. And then what do you get here? You can directly substitute. Notice I did not write limit anymore after that. And we get -5 as we've been getting in the previous things. Okay, so if you need to take a picture of these strategies, do that right now. I'll give you 5 seconds, then we'll move on and we're going to practice this actually. So I'll give you time to work on it. Alright. So here's some practice time. Use those strategies. Think, what do I need to do in order to figure out this limit, to evaluate this limit? Don't say solve, by the way, because you're not solving anything. Okay, so for this specific problem, I'm going to give you not 5 minutes. That's a bit too much. By this point, you should be able to do this within 3 minutes. By the time you get to the test, you should be able to do it within 2 if you're in a good place. So I'm going to give you 3 minutes right here. I'm going to set it, and then right after that, we'll go over it together. Alright, begin. Alright, so time is up. Let's look at this and go over it. So, what you should notice here is you have square roots. So which one should you always try? If you have square roots, you should always try conjugates, because that's probably going to be right. And actually, I mean, the reason for conjugates is for square roots. So let's do that. So what conjugate are we looking at? So we have two terms in the top. We have this thing. So we have the square root thing, and then we have the non-square root thing. So we're taking the conjugate of that quantity. No, you do not ever change the thing inside there. That is actually kind of useless. Because the purpose of the conjugate is so that you end up with this thing times this thing. Remember when you have a minus b times a plus b, that gives you the first thing squared minus the second thing squared. That's why we have conjugates. That's why we use them in this. So let me erase that real quick. Okay, that equals. So the first thing squared. This thing squared, the square root just cancels out. Minus the second thing squared is just 1. Oops. Forgot to write limit. Don't make that mistake on the test. If you do, just correct it as quickly as possible. Alright. So what can we do here? 1 minus 1 is 0, right? So we can do that. Alright, the limit as x approaches 0. I need to make this eraser bigger. Alright, x approaches 0 of... Now we have x divided by x times square root of x plus 1. All plus 1. What can happen now? Those can divide out. And we have the limit as x approaches 0 of 1 over square root of x plus 1 divided by... plus 1. So we can't really do anything else to it right now, unless we just conjugate it again, which it would actually undo everything we just did. So don't do that. Yeah, so now let's just direct substitution, see what happens. Does this work? Alright, 1 over... Because that's 1 plus 1 equals 2, so 1 over 2. We get something, so great. Okay, so now let's look over here. Let's see what we can do with this. So, I'll give you... This you should be able to do in... I'm going to put a minute 30 seconds. A minute and 45. Because this one is one of those ones that should be a lot quicker to do. I'll just do 2 minutes. But you should be able to do it within a minute-ish on the test if you're in a good place. So, 2 minutes, let's go. time's up. Let's look at this. So the first thing you should probably think of, even if direct substitution works, is you should probably factor this in because you got some things that are pretty easily factorable. Sorry, the sound was down. Yeah, so you should probably just factor this in no matter what, even if direct substitution is going to work, just because you have easily factorable things. So we got that. Actually, let me get rid of the timer just in case for space. Alright, and this is gonna be... that'll be x plus 1 times x minus 2. Alright, so let's see what we get then. Let's try direct substitution, see if that works. And it's also a lot easier with factored form anyway. So, you plug in 1 to each of these. We get, what's 1 plus 1? 2. What's 1 minus 1? 0. 1 plus 1 is 2. 1 minus 2 is negative 1. So you get 0 over negative 2, which is actually just 0. So, hey look, direct substitution worked here. So yeah, this one actually should have just taken like 30 seconds. Alright, whoops. How did I move that? Let's move on to the next one. So this one I'm only going to give us a minute and 30 seconds to do. The reason for that is we already... just look at it, you'll see that there's something... actually, I'll just put a minute on here, because half of it was already done. You'll see what I mean when you start doing it. Alright, let's begin. Sorry, the sound was down. Yeah, so you should probably just factor this no matter what, even if direct substitution is going to work, just because you have easily factorable things. So we got that. Actually, let me get rid of the timer just in case for space. Alright, so now let's look at this. This is going to be interesting. Alright, and this is going to be... that'll be x plus 1 times x minus 2. Alright, so what we got earlier... so let's see what we get then. X plus 1 times x minus 1 over x plus 1 for x minus 2. Let's try substituting. Actually, we see this divides out, so we have less things to deal with now when we directly substitute. 1 plus 1 is 2. 1 minus 2 is negative 1. So you get 0 over negative. Okay, so let's look at what happens then. So hey, look, direct substitution worked here. This equals, let's directly substitute 2 minus 1 over 2 minus 2. That equals 1 over 0. So this actually would be undefined. Or not undefined, the limit does not exist. And whenever you say DNA, you have to have a reason. So here, the reason is actually because it's actually, I'll just put a minute on here. Unbounded. Because if you were to actually graph the function, it would look something along the lines of this. And at 2, you're going to get something that's unbounded. Because they're both infinite no matter which side you come from. By the way, also notice how quickly I was able to graph that. So that's just noticing this has a parent graph of 1 over x, and it just things happens to it. So basically it's just from years of practice with this stuff. So if you practice, you'll learn it. Alright, so I'm going to move on to the next one. Take pictures if you need to. Alright, let's begin. Okay, this one might look a little bit wonky at first, but actually we've kind of done this in class already. So normally if it's a stream and I've shown you this thing for the first time, I'd give you like 3, maybe 4 minutes, probably 3. I'm just gonna give you 2 minutes in this case because you've already actually done part of this problem in class. You just probably didn't realize it. Alright, 2 minutes, begin. Alright, so what we got earlier, x plus 1 times x minus 1 over x plus 1 for x minus 2. Let's try substituting. Actually, we see this divides out, so we have less things to deal with now when we directly substitute. Okay, so let's look at what happens then. We substitute 2 minus 1 over 2 minus 2, that equals 1 over 0. So this actually would be undefined. Or not undefined, the limit does not exist. So time is up here, so let's look at this. And once we start going over this, you might start to realize what we've seen this in class. So, Alright, so let's try going over it like this. Limit as h approaches 0. Now, we can't really do a conjugate of this. I mean, we can, but that's not going to be useful. It just gives us bigger powers. We don't need that. Can this factor? Right, so let's try not really, like so let's not do that. H approaches 0. Now we can't really do a conjugate. So let's just do algebra to it. Let's just simplify it as much as possible. It just gives us bigger powers. We don't need that. So if we do this, we get x squared really, so plus 2xh plus h squared minus x squared. So this minus x squared is just that thing that was originally there. Let's just simplify it as much as possible. It just gives us bigger powers. We don't need that. All divided by h. So if we do this, we get x squared plus 2xh. Alright, so let's look at what we get here then. So this minus x squared is just that thing that was let's see. Oh, by the way, just a quick thing. X plus h squared. This is not x squared plus h squared. Just a reminder there real quick. So just make sure you know that, make sure you understand and remember that. So anyway, let's go back to it. Let me erase the badness. Just remember, puppy. What can we do here? So we see that there's an x squared. It subtracts with an x squared. And then just, I would say rewrite the next thing immediately just because you don't want to try to process too much and then lose things. We have an h and an h in common, so let's factor it out. By now, it should be pretty clear how you get that. Divide that out. And then we get the limit as h approaches 0 of 2x plus h. And then directly substitute h with 0. Then we get 2x. So, this is actually an instantaneous rate of change problem. So actually, let me color code that. Blue stands out here. So this statement itself is the average rate of change of f of x on the interval from x to x plus h. And that actually means that the entire thing here. So we took the limit of the average rate of change. This is the instantaneous rate of change of f of x equals x squared. Sorry, I should have written equals x squared here for clarity. Okay, so let's move on to next one. I can give us a few minutes on this. Okay, yeah, I know. You look at this and go like, OMG fractions, but it's okay. Practice. It's good for you. So I'll give you 3 minutes and 30 seconds on this. Let's get a bit of a challenge there. Alright, so do that, and then I'll get us back and work this out together. Alright, so time's up on that. Let's get back to this and look at it together. Alright, so you probably have started to see the pattern that if you have something like this, you can't really factor or anything like that. You have to just kind of algebra it. So let's just try that then. The limit as h approaches 0 of, how can we simplify this? So we have fraction over fraction, technically fraction. Usually you would think, oh, just multiply the top by the reciprocal of the bottom. Let's not do that just yet. Let's get one term on top first. So let's do common denominator. Yeah, I'm not gonna write it. You know what it is. So you get x minus, in parentheses, x plus h, all divided by x times x plus h. By the way, if you don't got it, make sure that you just somehow practice fraction stuff. Actually, I'll just show you. I mean, at this point, it should be pretty clear how to figure this out. Just common denominators, because, I mean, you're in pre-calculus and you're seniors. Just saying. Or juniors. So, we got that. Yeah. Make sure you can see that. Okay, so, I'm just going to, I'll write even this intermediate step. Just so that I can be very clear on how that works. So those get subtracted out. And then, okay, I'm going to erase this thing over here. We don't need it anymore. We shouldn't have needed it. But anyway, the limit as h approaches 0 of... Again, just write the entire problem right back down. Don't skip anything. You will confuse yourself if you do. Because there's just a lot of stuff that you need to deal with. Now you got fraction over fraction. Reciprocal of h is 1 over h. That can divide out. And then we end up with limit as h approaches, and let me make that an actual m. Negative 1 over x times x plus h. H approaches 0, that's so we can substitute it in there. We get negative 1 over x times x. In other words, negative 1 over x squared. So this is, you could also write this negative x times x to the negative 2 power. Because remember, negative powers means dividing. Alright, I partly threw that in there because I need you guys to start practicing looking at those things and the whole powers thing. And also because actually this is the instantaneous rate of change of the function x to the negative 1, or in other words, 1 over x. So what actually happens here, and you might have noticed with this, is the power actually does come down. So the power came down and you subtracted 1. Here, the power came down and you subtracted 1. So negative x, so negative 1 times x, and then negative 1 minus 1 is negative 2. Just saying, real quick. But yeah, so that's a pattern that'll be useful to notice later on. Alright, so rates of change, let's kind of talk about what it means, what they mean, and then kind of just go into a few quick problems with them. Oh, I just realized I forgot to take the timer off. Hopefully that didn't block too much. Anyway, so the general idea is that you're changing you're looking at how much your dependent variable changes based on a certain amount in the independent variable. So we have two types. There's average and instantaneous rate of change. So instantaneous, so at an instant, a specific point, versus average is over two points. So from here to here, let's just say your curve looks like this. What's the average rate of change? Versus on the same curve, we can ask, what's the rate of change here? Like only there. So you'd find tangent line, slope of the tangent line, then you got the average rate of change. I mean the instantaneous rate of change, sorry. So here's just a bit more on it. Here's actually the symbol that we normally use for average rate of change, which is the same for slope. Same exact thing. So rate of change over an interval, we look at the start and the end, see what happens. Instantaneous is, what if we took the limit as h approaches 0? So this is going to be f of x plus h minus f of x, all divided by h. So as that h approaches 0. Because remember we said that if we have x and an x plus h, the distance between the points is h. So we let h approach 0 so that we have 1 instant instead of 2. So let's practice a bit. Let's find the average rate of change of on this interval. So I'm going to give you about 30 seconds to kind of just like work on it on your own real quick, and then I'll go over it as well. Okay, so get the timer back up. 30 seconds, because by this point this shouldn't be too difficult. Alright, begin. Alright, so let's look at this then. Remember, it's just changing y, we're changing x. So f of 1 minus f of negative 1, all divided by 1 minus negative 1. Alright, so that's going to be 1 squared minus negative 1 squared, all over, that's 2. So notice we get 1 minus 1 over 2, which is 0 over 2, which is, you can just have skipped to 0 after this point if you wanted. So average rate of change here is 0. Which kind of makes sense if you look at the x squared function. It's basically saying what's the slope from there to there. That's a straight line. Slope is 0. So just a quick little concept check there. Alright. Instantaneous rate of change of the function. Specifically from here to there. So we're gonna work through some of these problems. So I'll just do the first one. And then I'll have you kind of just do the rest on your own / we check it. So this is going to be the limit as x approaches, h approaches 0, sorry. Of f of x plus h minus f of x. Yes, you should probably write this exact formula on your note card, because it will be useful, obviously, as you can see from the stream already. Okay, so don't forget to write limit. It's okay if you forget if you write it in after you realize it. It's not okay if you forget and just don't write it in ever. Alright, so let's algebra this thing. Limit as h approaches 0. Okay, that'll be a half x plus a half h minus a half x, all divided by h. So the 1/2 x's will subtract out, then we just get the limit as h approaches 0 of 1/2 h over h. Now the h's will divide out, and we just get a half. this should actually make perfect sense because this thing's a line with slope 1/2, right? So it makes sense then that the rate of change at every single point, which is the instantaneous rate of change, is 1/2. In other words, that's just the slope of the function. Alright. Let's move on to this. Actually, I'm going to kind of show you both this one and the next one at the same time so we can just save a little bit of time and work on both of them at the same time. Can you see both? No, not really. So it's going to be this, and then number 3 is going to be f of x equals negative x squared. So kind of think about what makes that different. Alright, so I'm going to set... let's just put 4 minutes for this in total. And then I'm just going to go over both of them right after. Because the stream's kind of been going on a bit longer than I intended it to. And I don't want it to get ridiculously long, especially when it gets to video form later on. Alright, here we go. 4 minutes, begin. Alright, so let's look back at this, and basically this is gonna be the last part of the stream. So we've actually already done number 2. Number 2 was done up there. So this is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And specifically, this is going to be the limit as x approaches h approaches 0 of x plus h squared minus x squared, all divided by h, which we actually did the work for already, and we get 2x. Back at this, and basically this is going to be the last part of the stream. Okay, so not going to show you that part since you already did it. But let's look at what's actually different here. This is actually going to be the limit as h approaches 0. So even though I wanted to save time, I'm still going to write this because I want you to get used to keep writing that. Continuously writing that. So this is going to be negative. So notice that the negative is not included with the squared. Otherwise it wouldn't exist. It's negative times whatever that thing is. And that red box thing is squared. So I'm going to do it like this actually. Minus negative. I'm just going to do that in parentheses. I normally don't want you to do that, but I'm just doing it for visual purposes right now. So if you're watching this without audio for whatever reason, then you're going to miss that and get marked down. Okay, so anyways, look at this. So what happens then is that negative happens outside, and then we get whatever this is on the inside. And here minus negative, that's plus. All divided by h. And then remember to distribute the negative the entire way. All divided by h. So we have negative x squared and a positive x squared. Those are going to subtract out. Doesn't matter if the negative is before the positive, still subtracts out the same way. Limit as h approaches 0 of. Now we have negative 2xh minus h squared, all divided by h. And I just realized the timer is in the way, so I'm gonna get rid of that thing. I should probably move the timer over here. Oops. Over here. Because I feel it's a bit less intrusive if I forget to remove it. Anyway, let's factor out an h, because they both have an h in common. And we get negative 2x minus h, all divided by h. You could factor out a negative h, but it's actually going to be useless in this case because you're going to actually put it right back there. Okay, so these h's will divide out. And we get the limit as h approaches 0 of negative 2x minus h, which equals, so when h goes to 0, we just get negative 2x. So in this case, the negative actually just made it so that you had a negative in front. But you wouldn't have been able to do that if you include the negative as being squared. This would be if you have the negative squared as well, which was the same thing as x squared. But since that is not the case, that's why we get negative 2x. That's why they're different. Alright, so that's the end of the stream. I think the internet went weird and not a lot of people are here. Or I don't think anyone's here just because it kept going in and out. So yeah, I'm just gonna end it here. And not take any questions because I can't actually see any. And yeah, so good luck. Do well on the test. I know you can do it, so yeah, prove me right on that, I guess. Alright, good luck guys. 頑張ってね。じゃあよ。